Thank you so much, Professor Lingwan Lu, for this kind introduction, although I don't understand Chinese, unfortunately. But yes, so it's a real pleasure to be here with all of you and to open this Warma Club reading group on higher order network, which higher order networks, I found it very, very stimulating and exciting field in network theory. So I structured this lesson in two parts. The first part will be mostly introductory and covering some work we have been doing on an important problem that is emergent geometry. And this is work of some years ago. And then in the second part, I will speak about most recent work, which is highly innovative, is at the interface between topology and dynamics. So let me start by introducing higher order networks. So higher order networks are characterizing the interaction between two or more nodes, and they come in different flavors. So you can have hypergraphs that are usually quite popular for this in network theory, but specifically in computer science. Then you have simplicial complexes that are more used by mathematicians, and they can allow to use the tool of applied topology and geometry to represent higher order network. And then there is recent interest in network with triadic interaction, when you can have one node regulating the activity of a link. So regulating the interaction between two other nodes, and this regulation can be positive or negative. So the interest in higher order networks arise by the fact that higher order network data are recognized as fundamentally important to understand complex systems. And for instance, in the brain, you can have 3 regions of the brain that are correlated pairwise, so forming 3 links, one with each other. Or you can have an activation which occurs simultaneously on the 3 regions of the brain. So this is really a many-body higher order interaction, and you represent this as a field triangle, not just by 3 links, but is a triangle itself. And this is the higher order interaction. And in social network and collaboration network, you can have collaboration of teams of more than 2 individuals, of course, or phase interaction of groups of more than 2 individuals. You have ubiquitously higher order interaction also in protein complexes. And in ecosystem, as well as neural networks, neuronal networks in the brain, you have this triadic interaction. So the fact, for instance, that one species can regulate the interaction between other 2 species and so on. So there really is still, the number of data is still moderate, I would say, but there is an increasing recognition of the importance of this higher order interaction to characterize the interplay between structure and function of complex systems. So I will follow mostly my recent book by Cambridge University Press, which is a small book which provides a general overview of the interplay between topology and dynamics of higher order networks. And so you are welcome to read the book and deepen your understanding of what I'm talking about later on. So there are two parts of this lesson. The first part is introductory, also because I'm the first lesson on higher order network. So I think it would be useful to define what higher order network are. And then I will mention some work, some line of work we have been quite active on the question of emergent network geometry. So when you look at higher order network structure, actually the picture is much richer than if you look just as a network. In a network, people have looked and consider mostly the combinatorial and statistical property of a network, for instance, the degree distribution, right? But when you look at higher order network, you can really enrich your toolbox with methods coming from discrete network geometry and discrete network topology. And this method coming from math, from applied math, can really help you understand the structure of higher order networks much deeply. We said that higher order networks can be hypergraph of simplicial complex. Let me define hypergraph and specifically mention the difference with simplicial complex. So hypergraphs are formed by hyperedge. So an M hyperedge is a set of M nodes, and they describe the higher order interaction. And so they describe the higher order interaction, and so they capture some structure of your data. And a hypergraph is a set of hyperedge. So a set of, as a graph is a set of edges, and hypergraph is a set of hyperedges. So it can include, for instance, a given set of triangle, and then some links, and some links might not be included in the hypergraph. What is the difference with simplicial complex? Simplicial complex are formed by simplices, which are the building blocks. So a 0 simplex is a node, a 1 simplex is a link, a 2 simplex is a triangle. So a d-dimensional simplex is a set of d+1 nodes. It describes the higher order interaction between these nodes. So to this extent is equivalent to a hypergraph. But it also allows a topological and geometrical interpretation of the simplex. So you can use a lot of tools in addition to that. So this is a simplex, and you distinguish between the phases of the simplex. The phases of the simplex are just the simplices that are constructed by subset of their node. So if you have a tetrahedra, the phases, or a 3 simplex, the phases are 4 nodes, 6 links, and 4 triangles, all the subgraph that you can form by that. So a simplicial complex is then a set of simplices, but has an additional property. And this additional property is that is closed under the inclusion of the phase of each simplex. So this means that if the triangle 1, 2, 3 is in the simplicial complex, then all its phases, so all its links, 1, 2, 2, 3, and 1, 3, and also the node 1, 2, 3 should belong to the simplicial complex itself. So this might seems like a constraint, because well, maybe you can have a collaboration network in a scientific collaboration network. You can have a paper between 3 authors, but you might not have a paper between each author of the triple. But as long as you know what you are doing and you are using the simplicial complex to represent your collaboration network, so the real interaction that you can really you really represented are all only the simplices of highest dimension that are not phases of any simplex. As long as you know what you are doing, it's totally fine to use also simplicial complex to represent collaboration network, and this opens the possibility to use a lot of tools coming from topology that are very useful. So the dimension of a simplicial complex is the dimension of the larger dimension of the simplices. So here you have this structure that is only formed by triangle and their faces. So the dimension is 2, the dimension of the triangle. And the facets are the simplices of a simplicial complex that are not faces of any other simplex. So here, for instance, all the triangle of the simplicial complex are the facets of this simplicial complex. So a pure simplicial complex is also a very useful notion. A pure simplicial complex is just a form of dimension D is formed by a set of d-dimensional simplices and their faces. So the facets have all the same dimension. And so you can describe this simplicial complex just by a tensor, which has d+1 indices. So for instance, here you have this two-dimensional simplicial complex, and is described by a tensor of 3 indices. And it will tell you, this tensor, if the triangle R, S, and P belongs to the simplicial complex, and then it takes a value 1, or doesn't belong to the simplicial complex. So it's an extension of the adjacency matrix to higher order network. And it's important to notice that you might have also simplicial complex that are not pure. So you can have also, in some cases, some facet, for instance, this link that is dimension 1, while the other facet of this simplicial complex are dimension 2. And in this case, we say that the simplicial complex is not pure. So they are not only simplicial complexes, because the simplicial complexes are built by this building structure that is a fully connected structure, a simplex. But you can also relax this. For instance, if you have a social network between a group of people, in the face-to-face interaction between a group of people, it might be that not everybody in the group know each other on a personal basis. So you can have, for instance, square or cube. So you can have motifs or building blocks that are less dense than simplices. And for instance, in 3 dimension, you have this hypergroup orthoplex and icosahedra and so on. So you can build a structure also with these less than simplicial building blocks that are, and this structure are called cell complexes. An important question when you have a simplicial complex is how to go back to a network, and then you have to retain only the node and the links. So you have a simplicial complex, you only retain the node and the links, and you get a network, which is also called network skeleton. And you can also do another operation. So you have a network and you want to generate a higher order structure out of it. One way to do that is to do what is called a clique complex. Every clique, any fully connected subgraph, is interpreted as a simplex. And then you have the simplicial complex that is formed, but you might, starting from a network, which is also, for instance, a scale-free network of just a scale-free network, which doesn't have higher order interaction. But if you do the clique complex, you might end up with a higher order network with very high dimension, because the scale-free graph is known to have cliques that can be very large. Okay, so you need to be careful when you do this operation, but this is something you can do. And in particular, you can also concatenate the operation. So you have a simplicial complex with your higher order interaction, you extract the network skeleton, and then from that, you do the clique complex. You can do that, but you need to be careful that the structure that you can get with the clique complex might not be equal from the structure that you started from, because the clique complex in some sense maximize the number of possible higher order interaction that you can have, while in reality some of this interaction might be missing. Okay, so one problem is, for instance, inference. Given a network, extract which are the through higher order interaction in the system. Let me start discussing also some combinatorial property of this higher order network. And of course, the degree is very important in a network structure. The degree is the number of links of each node. The generalized degree is a notion that can be used also on simplicial complexes and can be associated to phases of different dimension. So the generalized degree to 0, for instance, of this simplex, of the simplex alpha, is the number of triangle, two-dimensional simplices, incidence to a node, z-dimensional simplex, alpha, okay? And K21 alpha, similarly, can be the number of triangle incident to the link alpha, okay? So you can have, for instance, in this case, that a node 3 is incidence to 4 triangle, and the node 3 is incident to 4 triangles, so its generalized degree is 4. But the link 1, 3 is also incidence to 3 triangles, so the generalized degree of the link 1, 3 is 3. So let's go back to the case in which the simplicial complex is pure. So we have this tensor representing this structure. Then this generalized degree can be written in terms of this tensor. And is the generalized degree of a phase alpha is just the sum of dimension d, is just the sum of these adjacency tensorial elements of this tensor, where alpha prime is including the phase alpha. Okay, so you sum all the, let's say, triangle including the node alpha, or all the triangle including the link alpha. And these are not totally independent, but they follow nice combinatorial relation that you can work out. So interesting, as we will see, like in network, you say this network is scale-free, this network is exponential, and so on. But in simplicial complex, it might be that the same simplicial complex, the generalized degree of the node, is, I don't know, scale-free. The generalized degree of the link is exponential. So you have this statistical notion of the generalized degree distribution that depends on the dimension you look at. So, and there are also notion of connectivity. So you can have the zero connected component, which describe the component formed by nodes connected to nodes through links. And then you have the one connected components describing the components of links connected to links through triangle. And then you have the two components describing the component of triangle connected to triangle through tetrahedra, for instance. And these are very closely related to the notion of clique community that was introduced in 2005 in network science. So this is really very similar to the topological way of thinking. There are also geometrical properties. So one important quantity when you look at geometrical property is the incidence number of the d-1 phases. So you look at the d-1 phases and you do the generalized degree -1. So for instance, this link has a generalized degree 3, so has an incidence number equal to 3 minus 2 equal 3 minus 1 equal to 2. And then you want to know when this structure, when your simplicial complex is a manifold, because when you do geometry, you know, you want to relate, for instance, to the geometry in continuous space, and then you want to distinguish when your network is similar to a surface and when is not similar to a surface. And then you have combinatorial property to check that, in which the network should be d-1 connected. The simplicial complex should be d-1 connected, should obey also another property. And importantly, this incidence number should be 0 or 1. So let's see what is the meaning of that. So if you have in this case, this link was the incidence number was 2. So you have this kind of thinning forming in the structure. So this is not like a manifold, it's not like a surface. So this structure will not be a manifold. While if n alpha is only 0 or 1, then you can just start to understand that this is looks like a surface that is unfolding. And then you have the notion of curvature. There are many different proposals for that, but one of the most fundamentally established measure of hyperbolicity is Gromov hyperbolicity, which takes 3 nodes in your simplicial complex or in your network, looks at the shortest path between them, and then measure the smallest distance between the shortest path. And once that this smallest distance delta should be constant or small respect to the diameter of the network. So for instance, if you have a tree, right, you have these 3 nodes, and these are the shortest path between them. They cross at one point. So the distance between the shortest path is 0. If you have this NGF that we will define later on, and you have these 3 points, you build the shortest path, which are this triangle, and the shortest path are a distance at most 1. So these network are delta hyperbolic with delta equal to 1. Okay, you can demonstrate that whenever you choose the 3 node in this NGF, then delta can be only 0 or at most 1. So this is a measure of hyperbolicity. It's kind of saying it's not really like a tree, but it's going in that direction. It's a kind of a fat tree. So one question is how to describe network geometry and network topology, because data set point in the direction that actually that actually network might be really describing in many cases discrete topology and discrete geometry. So for instance, the fiber here in the brain really look like a manifold that is forming. This is a fungal network. So an important question is to understand this network geometry. And here we refer to a question which comes from theoretical physics, which is the question is the geometry of complex system a priori prerequisite for the network evolution, or is it an emergent property of the network dynamics? So is it possible to have purely combinatorial and probabilistic kind of rules that yet can generate a network which has an emergent geometry? And so we started with Xiao Wu, which was visiting my group in 2015 to think about this idea. And we describe a model that describes how two-dimensional simplicial complex can be constructed and generate emergent geometry. So our rule, our combinatorial rule, is that every link is incident at most to k bar triangle. And then we have 2 rules. This one occurs always. So at each time you choose a link and then you add the triangle to it. Or you choose 2 links that are adjacent to each other and you kind of close this pi. Okay. So the process A occurs always, and process B occurs with probability p equal to 1, and then you reiterate this process. And the structure that you get is a manifold for k bar equal to 2, which has a very interesting property because the curvature, local curvature of the node is heterogeneous. And then you have for k bar instead equal to infinity. So when you attach a triangle uniformly to link, you have an emergent scale-free network. Okay, so this is a way to show that there are simple combinatorial rules that yet can create a network with geometry. And then we went up on and study what happens if you can consider a process in higher dimension, not only with triangle, but also tetrahedra and so on. And so this is the network geometry with flavor that we have proposed together with Christophe Gramede. And in this work, you start with a triangle, a d-dimensional simplex, and you have growth. So at each time you add a d simplex and with a new node and attached to a d-1 phase. And this attachment depends on a flavor, which is a quantity that can take value -1, 0, and 1. And you choose this d-1 phase alpha with this probability here. So let's look closely at this probability. If S is equal to -1, you have something proportional to 1 minus an alpha. So if an alpha is 0, well, you can still, if this quantity is non-zero, so you can still attach a simplex to it. But if an alpha is 1, the probability to attach an additional simplex is 0. So in this way, with flavor -1, we really obtain manifold because an alpha can only take value 0 or 1. And for S equal to 0, you have uniform attachment. And for S equal to 1, you have preferential attachment. And then both an alpha can take any value. So they are not manifold. So in this kind of the manifold in 3 dimensions, you can see it also as attaching this tetrahedra to this triangle. And then it's like this triangle being triangulated in this way, a little bit like the Apollonian network move. And you can see that this network produces an emergent preferential attachment. Also, if you are in 3 dimensions and the flavor is -1, you have a manifold. So you look at this node in the middle. This is incidence to 3 tetrahedra and 5 faces where you can add additional tetrahedra to it. When you attach a tetrahedra, then it's incidence to 6 faces. So at the next time, I will have more probability to attach a tetrahedra to it. So more tetrahedra attached to the node, more tetrahedra I want to attach to the node. But this is not intrinsic in the model. It's just an outcome of the combinatorial associated with the dimension of the simplicial complex. So the picture is like this. In dimension equal to 1, you have a graph. So if you have uniform attachment, you have an exponential network. If you have preferential attachment, well, you have a BA model, a BA3 network, and the manifold is just a chain. Then you go up to 1 dimension, and with uniform attachment, you have a scale-free simplicial complex, and the manifold becomes exponential and small world. And in 3 dimensions, also the manifold becomes scale-free. So you have this effect of dimension, and you can really calculate with the master equation approach, the degree distribution. And you can show that for S equal to 0, as long as the dimension is greater than 1, the NGF are scale-free. For the flavor, so the manifold, you need a dimension greater than 2, and then the NGF are scale-free. Interesting, this is well confirmed by the simulation result, and the code are in my GitHub page. And interesting also the generalized degree, and this is what I was mentioning before, the generalized degree of the different phases of different dimension can have different statistical property. So if you are in dimension d equal to 3 and you look at the flavor -1, the triangle, we have a bimodal generalized degree distribution. So the degree of any triangle can be either 1 or 2, so it's bimodal. The link will have an exponential generalized degree distribution, And the node will have a power law and actually scale-free degree distribution. So the statistical property depend on the dimensionality of the simplex. And also these networks display an emergent hyperbolic network geometry. So this is the case of the manifold. So you start with the triangle, and then you attach triangle to links, and you get this structure that has a natural embedding in the Poincaré disk. So it's naturally hyperbolic, and is actually called a fairy graph, a random fairy graph. You can do the same in 3 dimensions when you have a tetrahedron, and then you stack tetrahedron to triangular face, and then you get this emergent geometry, hyperbolic geometry in 3 dimensions. Also, for the other flavor, where you don't have a manifold, you can prove that the structure are hyperbolic in the sense of delta hyperbolicity with delta equal to 1. So this is really answering a bit the question, what is a natural random geometry, right? So if you ask this question to a mathematician in the 60s, would say, well, a random geometry is a random graph. So you start with a fully connected network, and you put links randomly with probability P, or you remove, you retain links also only with probability P. Or you ask this question to a physicist, always in the 60s, they will say, well, is a percolation cluster in 2D. I start with my favorite square lattice, and then I retain link with probability P. This is my random topology. And then this picture of emergent geometry really tells you that when you have this combinatorial rule and a minimal set of combinatorial rule, what you have is really an emergent hyperbolic geometry. So it's like something growing in an hyperbolic space. And this is what is natural in this setting. So this is what I talked about. So this emergent hyperbolic network geometry. We have also additionally a very interesting set of works on maximally entropy model and of configuration model of simplicial complex. You find the code always in my GitHub page, which was in a previous slide. And I think this concludes the first part of this talk. I don't know if you want to ask question now, or should I continue, or should we stop in any case 5 minutes? Or
are there some questions?
Hi, Ginestra. I have a small question, but I have already chat with Professor Chen in the chat box, but I still want to see what you think that the main difference between the hypergraph and the simplicial complex. Can you explain a little bit more?
Yes. So the simplicial complex, you have this constraint that if you put a triangle, for instance, you should put all the links and all the nodes of the triangle in the simplicial complex as well. Mm-hmm. So for instance, if you have a collaboration network, right? Yes. And you want the collaboration network is, the data is in the form of an hypergraph, because you can have a triangle, but you might not have the links of this triangle as a collaboration, right? Mm-hmm. Of course, one way of doing this is to use a hypergraph, but you can also use the simplicial complex as long as you know that really the data that you're sure you are representing are the facet. So are the simplices that are not face of any other simplex. So if you have a collaboration between 5 people, mm-hmm. and these 5 people do not collaborate in any team of 5 and more people, then this is a true interaction, right? And
Yes.
and then, well, you keep in any case all the other phases. Also, if you treat them equal in the same, I mean, maybe there are multi-layer approach that could be used to have a simplicial complex in which you distinguish between these cases. But you know, typically in a simplicial complex, you treat, if you have 5 authors that have collaborated, you consider all the subset of these 5 authors as part of your simplicial complex. But as long as you know what you are doing, it's totally fine. And this will allow, in any case, you to use topological analysis, which is very, very useful.
Yes. So you mean that sometimes when we face some problem that is quite rough, then maybe the hypergraphs can give us some solution. But if you can know more details about the topology between them, or the interaction between the agents, and maybe simplicial complex can must give us a more accurate solution. Is it right? Or
yeah, well, in many respects, it doesn't matter, right? If it's a simplicial complex of an hypergraph. So for instance, if you have these models, right? These models of simplicial complex can be as well used as model of hypergraph. There is totally no difference with it. So you can stack them together. So you can have a simplicial complex of pure simplicial complex of only node and links, only triangle interface, only tetrahedra interface. Then you consider the aggregation of this, and this is an hypergraph, naturally. So from the perspective of many things you do with a network, and you might want to do as well with the higher order network, it doesn't make any difference. Then sometimes it does, and then if you know what are you doing, you can control. So it's a kind of tool and method that is fully controllable. So as long as you know what you're doing, that's totally fine.
okay. Okay, many thanks. Yes, many thanks.
Welcome.
Hi.
Hello.
Hi. Thanks for introduction. And I'm interested in the cell complex, and so I wonder what kind of objects can be better modeled by the cell complex. I know one example, just the molecule, the topology of the molecule can be modeled using the cell complex rather than a simplicial complex or a hypergraph. So I'm wondering if you know, is there other applications of the cell complex?
Yes.
Yeah.
So this relates also to the second part of my talk. I will not speak about cell complex, but I will speak about topological signals. So you might have dynamics defined on links, for instance, or on plaquettes. And for instance, in traffic, of course, you want to know the traffic on a link, right? And you want to know if the traffic goes around some street, right? If it circles around, or if it's going from the center to the periphery, or things like that. And in order to do that, typically you need the road network. And very often the road network is more like built by square or by pentagons than actually triangles. So for instance, in that context, it's very useful to use cell complexes, because you need to understand, otherwise you would have a hole, right? If you have a square and in a simplical complex, this is not filled because there is no triangle, there would be an empty hole. Instead, you want to consider it as full, and you might want to consider, going around the square. So in that context, it's very useful to do cell complex, and there are several words addressing cell complexes in the field of signal processing of topological signals. So this is, for example, one example, but of course, protein interaction network, protein complexes, and there is a bit use of complexes in different meaning, but protein complexes are formed by proteins that are not always pairwise interacting. No, they are aggregate, which are not always interacting pairwise. So maybe the cell complex is more opportune.
All right, thank you. One more question. Is there some kind of structure that can combine all this, such as some simplicial complex, cell complex, and hypergraph, utilize their, their flexibility and their
so
the hierarchical structure to, to model the.
The cell complex is a generalization of the simplicial complex. So the simplicial complex is included in the cell complex. Is the same thing. But yes, hypergraph are different. It's kind of a different language that is more used by computer scientists. And also this network with triadic interaction is a little bit different. Of course, yes, one would like to have a tool that allows to treat them all together. So for instance, for hypergraph, there are recent work by Jürgen Jost, which use some topology. It's not as rich as the topology you can do on simplicial complex, but it is starting to apply some topology to hypergraph, for instance, and this is of course quite welcome to do. So yeah, no, unfortunately we don't have yet the unification higher order model, but
okay, thank you, Ginestra. I must I'm so sorry that I must stop this question part, because we still have 70 pages. Yes, 70 pages. So let's Ginestra to finish her talk. Then we leave our questions later. Okay. Ginestra, please.
Okay, thank you so much. It's been good in any case to break with some of the questions which has arisen. So let me just move now to dynamics. So higher order networks, they have an interplay with higher order dynamics, which is mediated by combinatorial and statistical property, a bit like network, right? But also there are different modalities, and higher order network structure have topologies in simplicial topology and simplicial geometry that is reflected in their spectrum, and this feeds into the higher order network dynamics. So really the higher order network dynamics is affected by simplicial topology and simplicial geometry. And here I want to tell you just about this, how simplicial topology can be used to define higher order dynamics. So here is the second part of the talk. So we will have an introduction to algebraic topology, the operator and the spectral property, and then I will speak about this simplicial synchronization or higher order network, higher order Kuramoto model that we have proposed a few years ago. So, introduction to algebraic topology. So, topology is the study of shape. So you want to study holes and so invariant. So property that do not depend on stretching of your space. So for instance, the point is a Betti number 0. The Betti number 1 is like in the circle, you have a cavity. In a sphere, you have a two-dimensional cavity inside. And in the torus, you have both combination. And you can have data, for instance, this fungal network data, in which it's clear that one of is still a network here, but you can still understand that here the structure, in this structure, if you want to describe it, it's very important to characterize the statistic of these holes. And there are different methods to do that. And in order to do that, you need to use topology. And in topology and algebraic topology in particular, a simplex that we have defined before, it also admits an orientation. So you can have a link and you represent as ij, and you give an orientation. Here the direction is the orientation, is not the direction really, but the orientation I to j is different and is opposite to the orientation j to I. Similarly to a triangle, you give a clockwise or anti-clockwise orientation, and they have opposite sign. So with this structure, you can construct M-chain. What are M-chain? Are element of a free abelian group with the basis, the M simplices of the simplicial complex. So you take the simplices as your basis of an oriented, of a linear space. And then you have linear combination, which coefficient are the integer. So for instance, you have one chain is a linear combination of links with integer coefficient. So you have 1, 3, okay, then minus 2, 3, which is 3, 2. And then you have 2, 4, and you go to 2, 4. So you can represent this linear combination of link either as an algebraic object or as a topological object. And you have a boundary operator, which is an operator that acts on this linear space of M chain and produce a chain dimension M minus 1, and this is the definition. So let me just go to an example. If you apply the boundary operator to the links, you have node 2 minus node 1. Okay. If you apply the boundary operator to the triangle, you have a linear combination of the link at its boundary. So 1, 2, allowing these simplices to have the same orientation of the triangle. So this the orientation induced by the triangle. So you go 1, 2, 2, 3, minus 1, 3. So you go from 3 to 1. Okay, you go around that. So this is why it's called the boundary, because it maps the triangle to the link at the boundary. And interesting, there is a topological rule that the boundary of the boundary is rule. So if you apply the boundary of the triangle, you find the 3 links at its boundary, and then you do the boundary of these links, and the boundary of a closed chain is 0 because you go back to the origin, right, in the triangle. So the boundary of the boundary is 0, and you are welcome to do this calculation on your own to convince yourself. So there is nothing to worry too much about this boundary operator, because we can just represent as matrices, and these are rectangular matrices. So you represent the node as the row, for instance, of B1, and the links as the column of B1. And then for each column, you have the boundary of 1, 2 is minus 1, plus 2. So you have -1 here and 1 here, and you do the same for every link, and this is the incidence number B1. And for the triangle, you have a matrix in which you have the links here and the triangles here, and in the element of this column are the boundary of this triangle. So 1, 2, -1, 3, +2, 3. Okay, so we can work with this boundary operator and these incidence matrices. And since the boundary of the boundary is null, if you concatenate this incidence matrix, you get 0. And interesting, you can do homology. So you can study the homology class of this thing, and from this you can have an expression for the Betti number, which we have demonstrated before. But this is not very important now for this talk. But in any case, if you have this algebraic method that gives you the Betti number, a very popular way to characterize the structure of a simplicial of higher order network data, for instance, is if you have a point cloud, you put a radius around these nodes of different, a ball of different radius, and you see when this ball cross, and you build a simplicial complex out of it, and you monitor the cycle. So you monitor the connected component, you monitor the cycle. For instance, this cycle is quite long-lived, and then at a certain moment, this cycle is filled, and then you have only one blob, right? And then you measure as a function of this radius how many connected components, and for instance, a cycle, when it started and when it ends, as a function of the radius increasing. And this is a very popular because this gives rise to what is called persistent homology. And the idea is that the feature which persist for very long radius are very significant in your system. And this can be do for point cloud, but it can be also do for weighted networks. So you change the weight of the network and you monitor this cavity, how long they persist in the network. And there are beautiful work also by Giovanni Petri about this. So we have used a little bit this technique to characterize also locally what happens in a network. So in a network, we know the degree and the clustering coefficient are very important. So if you look at the node and its neighbor, so the neighbor and the links between the neighbor, you can see that and then you remove the central node, you see that the number of nodes in this simplicial complex is the degree of the original node. And the local clustering coefficient of this network here, is corresponding to the density of links in this simplicial complex. So you can study when in a different neighborhood in a data set, which have similar number of nodes corresponding to similar degree and similar clustering coefficient, but they might be having a different topology. So really in different data sets, this neighborhood, also if they have comparable n and rho, they might have very different topology. And this reflects some property of the different data set that you want to study. And of course, road networks are, for instance, very different. Another thing you can do is try to look at this pipeline. You know, you have a higher order network, but maybe is unknown, and you have only access at the network skeleton, and then you want to reconstruct the higher order interaction. And then we propose a method using the community structure with Sangutta Krishnapa, using the community structure of the node in order to reconstruct which higher order interaction are the true ones. So you can compare the community structure of the ground truth, for instance, of the Zachary Karate Club community structure, with the higher order community structure of the simplicial complex that you can reconstruct. And you can do this higher order community structure as a function of which simplices you really include or don't include in the simplicial complex, which clique you fill and which clique you don't fill. And then you, by minimizing the distance between these two constructions, the ground truth and your construction, you can see that, for instance, in the Zachary Karate Club, there is a triangle that is likely to be missing in the higher order network structure. This is regarding the structure. So you can use topology to study the structure of higher order network. And this is very interesting and very promising, but you can also use it to study dynamics. And in order to do that, you can use the Hodge Laplacian or the Dirac operator. So you are really interested now to understand topological signals. So topological signals are dynamical variable, not only associated to the node, like you are used in a network, but also associated to the links or to the triangles. So you really make the simplicial complex alive by allowing the dynamics to take place on every simplex. So there are not many data, but there are increasing examples of topological signals. So an example is a citation of a collaboration network. So you can have a team of 3 authors that have a given set of citation that is different from the citation that just 2 authors have. Okay, so you have also speed of wind in the ocean at given location. So the speed of wind, you have a triangulation of the Earth, and you can project the wind on the links. So you have a signals on the links indicating the wind or the current of the ocean. Or you can have synaptic signals between the neurons or edge signals in the brain also that are quite important. So it's really growing, and there is a really interested in these topological signals. So how to treat it? So the answer is with Laplacian. So the graph Laplacian is a well-known operator that is used to characterize diffusion from node to node through links. And it can be expressed as a boundary incidence matrix B1 transpose. And this shows that this semi-definite positive, and yeah, so that is semi-definite positive because the eigenvalue are mu square, where mu is the eigenvalue of the singular value of B1. But you can use also higher order Laplacian, and higher order Laplacian describe diffusion from n simplices to n simplices. And you can go either one dimension down, so you can go from link to link through node, or you can go from link to link through triangle. And so the higher order Laplacian is distinguishing the ln down and ln up. In one case, you go one dimension down and then back up, and in another case, you go one dimension up and then down. And the dimension of the kernel of the higher order Laplacian is the n Betti number. So from this, you can calculate the Betti numbers. And there is an important property of this higher order Hodge Laplacian is that the signals on which they act can be decomposed into 3 components. The harmonic component that goes around the cavity of the network, this n-dimensional cavity. You can have a gradient flow, for instance, for a link, a gradient flow going out or going in with sink and or sources, or you can have a solenoidal flow. So signal going around simplices. Okay, so this allows to treat signals of a given dimension, and there is a lot of progress. We have made a lot of progress with the Kuramoto model with that, and there is also a lot of activity in signal processing. So another question is, can we use an operator that couple signals of different dimension? And the answer is yes. And there is this topological Dirac operator. So the topological Dirac operator acts on a spinor. So you have a 0 cochain and a 1 cochain. So a vector which has the first block defined only on the node of the network, and the second block defined only on the links of the network, for instance. And then the Dirac is a bit the square root of the Laplacian. So it is acting when you have a signal on the links, it projected on the nodes. And when you have a signal on the nodes, it projected on the links. And it's such that when you do the square of this Dirac operator, you get the Laplacian. Okay, so this is very nice structure that couples the signals on the nodes and on the links, for instance, of a network. And you can really represent this eigenvector of the Dirac operator with color defined on the nodes and on the links of a fungal network, for instance, or another fungal network here. And you can do that also for simplicial complexes. So you can use now 0 cochain, 1 cochain, 2 cochain, 3 cochain. So function defined on node, links, triangles, and tetrahedra, and then you have a square matrix acting on this object and couples links, nodes to links, links to triangles, triangles to tetrahedra, and so on. And really, you can have a very rich spectral property of this structure, and really you can use this to couple nodes, signals defined on different dimensions, and as we will see later on. So let me now move to the use of Hodge Laplacian to study higher order Kuramoto model. So let me just first tell you a little bit about the Kuramoto model. The Kuramoto model is a fundamental model proposed by Kuramoto in 1975 to study synchronization property, and synchronization is a fundamental dynamical process characterizing the dynamics of neurons, of fireflies, and so on. So the Kuramoto model assumes that on each node there is a phase, and each phase is oscillating at its own frequency, and the frequencies are different from node to node, so that everybody is independent on the other one. And then when you have a network, the link of the network are used to couple this phase with the coupling constant sigma, and then the phase tries to align each other. The phase try to align to the phase of nearby phases through a non-linear coupling, that is this sigmoidal coupling here. And the frequency are drawn from a distribution. You can choose the distribution in different ways. What we use always for now is the Gaussian distribution. So from this Kuramoto model, you can use the global order parameter R, which is this quantity, and you have a transition between 0 and non-zero transition. So the non-zero transition means that the systems start to synchronize together. So at least a finite fraction of the nodes start to synchronize together. And this is this phase transition. And this 0 is 0 in the infinite network limit. In a finite network, you will see something that is slightly non-zero, but this is very much established. So how can you define the higher order Kuramoto model for signals defined on the links? This was our question. How can you extend the notion of the Kuramoto model to higher order topological signals? So, and this is the work we have done with Ana Paula Millán and Joaquín Torres in 2020 in PRL. So we are interested in signals, for instance, defined on the links, on the triangles or tetrahedra and so on. So first of all, we notice that the Kuramoto model can be written in terms of the incidence matrix. Now, theta is the vector of the phases associated to each node. Omega is the vector of frequencies associated to each node. And then you have B1 and B1 transpose, the incidence matrix, and this sign of this vector is taken element-wise. Okay, so this is just another way of rewriting the same equation written by Kuramoto in 75, essentially. Well, for a sparse network. And what we want to do is to now interpret, write another equation which can capture synchronization of topological signals. So signals, for instance, defined on the links or on the triangles. And what we do is we practically allow this nonlinear coupling to also couple signals through node, through n-1 dimensional simplices or n+1 dimensional simplices. So you can go either down or up. From link, you can go through node or you can go through triangle. And this is the equation we come up with, which is a straightforward generalization of the previous equation of Kuramoto. And the linearized version of it will give you the Hodge Laplacian. So also the linearized version will keep an intrinsic higher order nature. So in order to see an example, for instance, this is an example of the dynamics on these links of this simplicial complex, and you really have many body interactions. So you have interaction between the phase of three links here inside this triangle, and increasing the sign here of the sign of this linear combination is not decided a priori, but is only determined by topology. So the topology and the orientation of your simplicial complex automatically define this non-trivial choice of this sign. And a question that we ask, if you have these dynamics that define on n simplices, so defined on links, let's say, what is the projected dynamics defined on nodes or on triangles? So if you have the dynamics defined on links, is there a way to project these dynamics on triangle or on the node? And the answer is yes, there is. So the answer is that you just use the incidence matrix and you do either a discrete curl, for instance, of the signal of the links, or a discrete divergence of the signals on the links. And the dynamic equation of this projection decouple, and then these two projected dynamics can really synchronize independently. So you have practically the solidonal and the irrotational component of the signal that synchronize independently. The harmonic component is not touched by the dynamics. So in this way, if you look naively at the overall signal, include irrotational, solidonal, and harmonic, you would not see the synchronization. You really need to filter out the irrotational and solidonal component. And another way to sort it out, to filter out, is by applying the ln down and ln up operator to the signal. So really, you need topology to kind of detect this higher order effect. And what we went on and studied if it was possible to couple these two dynamics, the rotational and the solidonal dynamics. And what we did is we modulated the coupling constant of the part that affects the solidonal dynamics with the order parameter of the rotational dynamics and vice versa. And in this case, the projected dynamics are now looking similar to before, but we have an additional modulation of the coupling constant in the equation for the dynamics projected on n+1 phases, modulating with the order parameter of the n-1 phases, and vice versa. For the n-1 phases, we have a modulation with the order parameter of the projection on the n+1 phases. So now the dynamics, irrotational and solenoidal, are coupled, and the transition becomes explosive and discontinuous. So really, the transition becomes discontinuous. This is done, simulation done on the configuration model of simplicial complexes. We have, and this is also in this other technique by using Ln down and Ln up. And this is a simulation on real connectome of Homo sapiens and C. elegans. And we see this explosive transition also in this real data set. So we also collaborated with Juan Restrepo, Joaquin Torres, and Reza Gombasham on coupling signals that really are defined from the beginning on the node and on the links. And what we have is a dynamics of the signals on the node, and then we have this adaptive coupling depending on the same signals of the links projected on the nodes. And we have a signals of the links, so okay, coupled with the signal on the nodes. And in this way, we have that both in NGF model or in the simplicial configuration model, we have a simultaneous explosive synchronization of the signals of the nodes and of the signals of the links. So the signal of the links projected on the nodes and the signals of the links projected on the triangles. They all synchronize explosively at the same time. And for Poisson network, we have a theoretical understanding of this transition, which is really discontinuous, the backward transition and also the forward transition. But the backward is discontinuous and stable. And we have this theoretical prediction using the annealed approximation, which works pretty well. The forward transition is depending on the network size. So and then we went really on, and we use instead of having this adaptive coupling, that is a global coupling, in which you have the coupling constant between these topological signals depending on the global order parameter of the network. We wanted to have a model which couples the signals of the nodes and the signals of the links only locally. And then to do that, we use the Dirac operator. And in that case, we found a really thermodynamically stable hysteresis loop with a continuous forward transition and discontinuous upper transition. We find also that the order parameter are really not only defined on nodal links, but are defined on linear combination of the signals of nodal links. So it's really very much entanglement between these two dynamics. And this Dirac synchronization also leads to a rhythmic phase in which the order parameter acquires spontaneously a phase in the rotating frame. So really, we believe that this might shed some light on topological mechanism for the emergence of this brain rhythm. So this, I'm almost finished with my talk, and in general with the discussion about how topology affects dynamics. But I wanted to tell you also a little bit about this direction, the combinatorial direction, and just flash some work we have been doing over the years. So one thing that we have been doing, which is quite interesting, is the role of hypergraph to model collocation in epidemic spreading. So you might have, in epidemic spreading, you might have environment such as a ship or restaurant, which are the environment in which epidemic spreading occurs, and a different individual go from environment to environment and have a different time of exposure. So you go to the supermarket for a certain amount of time, or you go to the restaurant for another amount of time, and there the epidemic spreading can occur. And we have combined this higher order picture of epidemic spreading with epidemiological insight that actually, in order to get the infection, an individual requires a minimal to receive a minimal dose. And then by combining the fact that the exposure time might be very heterogeneous and that this threshold mechanism, we see that the interesting result that in some case the probability of infective infection might be non-linear and actually superlinear with the number of infected individuals in a neighborhood. So this might explain some of the super spreading event occurring in some data set, particularly in COVID. Then we have also this picture of multiplex hypergraph. So you can have you can combine kind of pure simplicial complex model like a network, simplicial complex just formed by triangles, and then you can aggregate it in this picture and form an hypergraph. And with this multiplex picture of your hypergraph, you can also study cooperative behavior, which occur in this multiplex network. And this is a fantastic work by my student Anlin Soon. And then I'm very excited about the work which is just submitted. So I choose not to speak about here because this is not accepted yet. But triadic interaction are very interesting. So you can have one node affecting the interaction between other two nodes and determining this the state of this link either in a positive way or in an inhibitor way, so in an answer way or in a regulated positively or negatively. And this can turn percolation, so the fact, the connectivity, the fact what is the connectivity of the network in presence of this regulatory interaction can turn percolation into a dynamical process. So instead of having a single second order phase transition, you have an order parameters, the node in the giant component of your network, which undergo a root to cause. So you can have that dynamically due to this regulation. The system might be in two state with a giant component 40% and a giant component 20%, and then intermittently go from one to another, but also can have a dynamics which is much richer and have a very different value of fraction of node in the giant component with time. And here I have a movie. So you can have a network that, given the regulation, evolves in time with a giant component that is time dependent. So this is really the fact of having percolation type dynamics and then a regulation of this triadic interaction and then a percolation dynamics and a regulation again. And this can lead to this very, very rich structure that really turns percolation into a fully fledged dynamical process. And this is fantastic work by my student Anlin Soon and collaboration with Filippo Radicchi and Jürgen Kors. So I reached my conclusion. So here, this is the conclusion to the second part. So simplicial synchronization is really able to capture the synchronization of topological signals of higher or higher dimension. And it can be detected by monitoring the irrotational and the solenoidal component of the topological signals in separation. And you can also use Dirac operator for Dirac synchronization, that is coupling locally topological signals of different dimension, which can become explosive and can give rise to a rhythmic phase. Thank you so much for your attention.